There we go. Here. Oh, I don't want that. Close that. Sorry, un momento, por favor. Oh, come on. There you go. All right. And it's so it's not expanding my screen. So I guess I'll have to just drag it larger. There we go. All right. There's only a couple more. Like I said, there's really only a couple more. It's another special problem, highly likely to come up in some way, shape, or form, or in multiple ways, shapes, or forms on one exam at the end of the year. Let's see if we can focus. There we go. So this special problem is actually fairly easy in my opinion, and obviously once you find how to do it. This is almost always what it looks like. They have a box, they have a rope, they have another box. They'll call this, M1 probably. They'll call this one M2. And let me zoom in for the guys that are here so you can see that a little better. In fact, let me shut one of these lights off. Better. So this is a problem, and then they say there's somebody pulling it with the force off to the right. So, kind of object. It's not really an object, sorry. The system starts from rest. And begins moving due to applied force F. I mean, it's just a general idea. Got something sitting there. I guess it would be slack, of course. The rope would be slack, but who cares about that detail? The bottom line is that once somebody starts to pull it, and then there would be some tension in here, and these things just start moving rightwards. All right. Let's start with their. It's not really a question, I guess, either. It's just a statement. System starts from rest and begins moving due to an applied force F. Okay. The first question might be, of course it would be. Of course it would be a free body diagram. If this were a free response question, and it does show up. This has been a free response question many years. No guarantee, of course, which ones you'll get on any given year, but this is one of the ones I like. Okay, so you can try to think about it yourself, maybe. So it's not just a copy what I do, but you can think about it, try it yourself. What would the free body diagram look like for that scenario that I've drawn? Oh, I'm so sorry. I meant to say, just so you, well, which would be the case even in the case if they don't say anything, then you assume no friction, which is what I did. I didn't say anything, so you would have assumed no friction. That's not really my style, though. Like I make a problem. I like to just be very specific. They are actually not always very specific. So if they don't say anything, then you again just assume no friction. If there is friction, they will definitely say there is friction on this surface. So this is assuming there's no friction. So even though it's moving rightward, we know that the weight of each block will be perfectly balanced with the normal force for both of them. If there's no air resistance, there's no friction, there's no resistive things, and we know if the motion is to the right, any resistance to that motion would be to the left. And again, in the real world, it just comes down to air resistance or friction. Some sort of interaction with what's in the environment. What's in the environment? The floor that you're sliding on and the air that you have to move through. But we're assuming there are none. There's a floor, but there's no friction. There's no air. All right, so there's no leftward forces to be shown. There's just one rightward force to be shown here, which would be represented as the tension force. This is for M1, by the way. This one would be for M2 over here. So whenever you're referencing the rope force, you just write FT for tension because it's got a certain tension in it and that has a certain direction. FT. That's it for him. Just make sure, are the forces unbalanced? Because you know he's going to move. So if he's going to start moving and he's probably going to accelerate, right? Then you need to be drawing a free body diagram that's unbalanced. If you know in your mind that it's accelerating, yet you've drawn a picture that shows balanced forces, then you need to catch that and be like, wait a second, my idea doesn't match my diagram. We know that the forces need to be unbalanced. Yeah, this is unbalanced. These two are balanced. How about this other guy? As he's being pulled to the right with some force F, which I certainly can label here. And again, I'm not making the length of these, like this F has to be longer than Fn or shorter than, and who knows? I have no idea whether this vertical Fn and this F, how they compare. I don't know. They didn't give me enough information to make that judgment call. I do know that however long I make mg, I should make Fn the same because those have to be balanced, right? So that makes sense that when you're on an axis, you got to think about how does this one compare to this one. But to say how does Fn compare to F, I mean, who knows? They didn't tell me how strong F was. So, but who's pulling back in the other direction, right? Yeah, the rope. Yeah, exactly. If you think about this thing as being pulled, you can think of it this way, right? This rope, when this thing gets pulled, this rope pulls on M1. We already indicated that here, right? This rope, again, in this section, pulls to the right on M1, making M1 move to the right, right? But Newton's third law says that if this rope pulls on M1 rightward, then M1 must pull on the rope which way? Leftward. That's Newton's third law at its essence. Again, the idea that you see this thing moving to the right immediately indicates that the rope must be pulling it to the right. This M1 has no idea that M2 is there. They're not alive. They don't have brains. It has no idea that M2 is there. It has no idea what's driving this thing in the front of this front over here. All it knows is that there's a rope pulling it to the right. It feels that tug. And for that reason, it moves that way. And again, that rope pulls on M1 to the right, and therefore M1 must be tugging on that same rope to the left. And that means in this section here, right here, there's a leftward pull. There's a pull in the backwards direction on M2, right? So I'd have to indicate that there's a tension that is this tension in this rope is acting on both of these. It's acting rightward on M1 and it's acting leftward on M2. And also remember that the tensions always have to cancel. So if you thought that the tension on M1 was to the right and the tension acting on M2 was to the right, those wouldn't cancel. The two ends of a rope always have forces that are canceling. That means one side has to have leftward force and the other side has to have rightward force, and they have to be equal in amount so that they're fully canceled. Full cancellation there. So with that in mind, I would just draw FT. And then just think to yourself, is it, and again, these matter, right? How long this one is compared to this one matters because they're along the same axis. Is it unbalanced? It has to be. It's moving to the right. We know that as soon as he tugs, if this was a person tugging, it's going to accelerate to the right. That means there needs to be extra force to the right. So I'd have to be careful about that one. I'd say, yeah, it seems good, right? F is longer than FT. Which direction is the extra force? The net force is to the right. All right, good. And technically, technically these would be the same. If you really wanted to pay attention to the details, these would be opposite in direction, equal in a magnitude, indicating that the overall tension force that the rope provides to the system as a whole is technically zero. It provides a leftward force to the guy that's on the left. It provides a rightward force to the guy that's on the right. What effect does that have for the whole system as a whole? None. Because those, as a system as a whole, those are internal forces that fully cancel. The only thing that's really causing this motion is this guy in the front. Who is this? I don't know. We don't ask that question. Something is pulling. All right. What's the most common next question? Derive a formula for the acceleration of the system. Note, as soon as you see those words system, you think system approach. Because again, there's people on YouTube that do this problem and they spend 25 minutes doing this to get a derived formula that I can teach you how to get it in 1.5, not even, in less than 1 minute. I mean, granted, when they're doing it on their own, it probably doesn't take them 25 minutes, but they're explaining it and teaching it, and it takes them 25 minutes to explain and teach how to do it some other way that even professors in colleges show. Don't do that. Just look at the system approach that I've taught you already. You do it in less than a minute. What is the system approach? Remember, the acceleration of the whole system equals the net force on the whole system divided by the total mass of the whole system. A equals F over M, which in general, F net, it's the net force. Come back to your free body diagrams. Again, connect with the fact that these have meaning. They have usefulness. Not all students make that connection. They just know that there's this thing called FBDs that we do. And then when they get to the equation part, there's no connection between the equation and the FBD. I'd be like, no, that's not right at all. There's a huge connection between the diagrams that you draw and Newton's second law. Huge. And if you make that have that understanding, you realize you can use these to develop what you write down here, right? In which part are we referring to? The net force part. The net force information comes from these diagrams. This is the whole system. So again, which ones cancel for this guy? These guys cancel. Boom and boom. Those are canceled. For this one, these cancel. Boom and boom. The tension is equal amounts of force but opposite direction on both. So those cancel. Boom and boom. So that means we only have one unbalanced force. F. The total mass of the system is just M1 plus M2. Because F is unbalanced. If there were some friction, and there could be, we can talk about that maybe later, then that friction would be in the leftward direction on both, because both blocks are sliding on a frictional surface. There would be a leftward force of friction on the first guy, a leftward force of friction on the second guy, and then you'd have to consider that. But right now, we're not. The next most common question is, derive a formula for the tension in the rope. while the system is accelerating. This is, of course, of importance, right? In the real world, again, what this real system is, who knows, who knows what it is? Is it the conveyor belt that people hold on to and they're going up the hill and they're skiing and people grab onto the rope? I don't know, it could be. Is it something else altogether that's a little more complicated and this rope isn't an actual rope, it's actually a chain, and then a chain is actually connecting truck 1 and truck 2? Yeah, and that's how physics works. Right? You make connections with things that look like this, with real world things. And the point being is that you don't want that thing to break. The quicker you want to speed up. Like, let me point out, if this was a super thin thread, like really thin thread, and there was a rope over here that you could grab and pull, and I said, accelerate, grab this rope and pull both of these to the right with this little thin thread here, but make sure this guy doesn't break. If he breaks, you failed. I want you to get him from this side of the room to this side of the room as quickly as you can, but make sure that string doesn't break. Thin little thread. Most people would go, they pull a little bit, they'd see the tension start to get tight right here, and then they would, okay, and they slowly start pulling. They already know not to accelerate it at too great of a rate, because if you decide to grab it and just yank it, boom, this thing is snapped. Instantly, it snaps. Why? Because you tried to accelerate it too quickly. You try to accelerate something that requires a force. Which force is required to accelerate M1? The tension inside there. If you pull it at a huge acceleration and you say, wow, that acceleration requires a lot of force, like 50 newtons of force, and you're like, but that little string actually breaks after a tension of 2 newtons, it snaps. That means you can't accelerate it that rapidly because this will snap and you'll be left behind and you failed, right? Because the challenge was to get them both to the other side of the room, for example. So that's my point, is that there's some connecting thing and it has a point that it breaks at, where when the force reaches a certain value, it breaks, then that force is limited to that breaking tension that breaks, and therefore the acceleration you accelerate the whole system at would have to be limited as well. You can't just try to accelerate at any crazy rate you wish. Same thing with toilet paper, right? Toilet paper, typical toilet paper on the wall, you got the roll, you got the little piece dangling down. If you grab that piece and pull it too quickly, it rips, right? You know that because there's something that has weight behind it, which is the whole roll above it. And if you pull, on the other hand, more slowly and have a slower acceleration, that thing will start rolling and the paper won't rip. But again, if you pull too quickly, it rips because it can't sustain that kind of force. All right, anyways, coming back here. To do this problem, to answer their question, which is about the tension. Just keep it simple. Which has the simplest free body diagram? Once you're doing the second part, which is, find the tension formula. Which one is a little more complicated than the other? I mean, this has 4, this has 3. So pick whatever's the simplest. This one's simple. So I'd say, all right, for this guy, can I write just right next to it, just so you make that connection, that the net force on him in the x direction equals his mass times his acceleration? Because that's what Newton said. Isaac Newton said, my law works for systems, it works for individual objects, it doesn't matter what you apply it to, it works. All right, so you say, I'm going to apply it to just this guy. Just this guy. The net force on him in the horizontal direction should equal his mass times his acceleration. What is the net force on him? This is unbalanced. For him, these are balanced, and this is unbalanced. FT. Right? So the tension in this rope must be equal to whatever his mass is times whatever his acceleration is. So coming back over here, you'd say if Ft is equal to m1 times his acceleration, based on what I was just describing to you, and you already know that the acceleration was derived as F divided by m1 plus m2, then and remember, whatever his acceleration is, he has the same acceleration. It's like other people in the car. You and your brother, if you're in the car, have the same acceleration because you're in the car. Every object in the car accelerates at the same rate. Not all objects feel the same force. Lighter ones will feel less force from the seat that pushes them forward. Heavier people would feel more force behind their back from the seat pushing them forward because, well, heavier things require more force to accelerate. Lighter things require less force to accelerate, assuming the acceleration is the same for both. So although the forces might be different, the accelerations are the same. Whatever rate he accelerates at the same rate. They move together. So you'd say, well, I know his acceleration is this, F over M, so just plug it in. The tension would be M1 times, in parentheses, F over M1 plus M2. And, in magnitude, you can certainly put your magnitude symbol around it if you want. So that's really all I have to say about that, because that's usually the extent of their question. I would like to just throw some numbers in real fast, if I could. Let's just say M1 was equal to M2, because it looked like they were. They're the same mass, and they're both, I don't know, 5 kilograms, let's say. Let's just put some numbers in. I just want you to get a sense of that. And let's just say that applied force was, I don't know, say 15 newtons. So this is me again, just doing the numerical part with you, just so you see it. So what would the acceleration have been in the beginning when we got the acceleration? F, the total force to the right divided by whatever the inertia of the system was, M1 plus M2. So it looks like numerically I would get my force was 15 divided by 5 plus 5. Equals 15 divided by 10, which is a 3-to-2 ratio, which is 1.5 meters per second squared. Okay, so then I know that the acceleration, again, is the acceleration rate, 1.5. If they had asked me that, I really don't think they would, but that's how you would do that. Just plug the numbers in. And then when you get to the tension part, this piece is the acceleration, right? F, we just said that the acceleration is F over M1 plus M2. F over M1 plus M2, it is the acceleration, just 1.5, we just calculated it. Times what is his mass? This original guy that was hanging out in the back. Well, I had said in this example, they're both 5 kilograms. So that's 5, so tension is 5. So that means the total tension in the rope should be in magnitude equal to 7.5 newtons. So that's how that goes numerically. Again, I don't know that they ask that often about numerical things, but they do, sometimes they do. It's not 0 times, sometimes they do. Usually it's about formulas though. All right, any questions on that one? All right. I think what I'm going to do is, I think I'm going to just pull forward because I have to. Just have to. That's how it is. Time that we have this year. I'm going to probably do the elevator problem with you now, or maybe I could give you guys some time to talk about. Maybe I'll do that. I'll just switch it up. I can do the elevator problem, maybe a video during my prep today, I guess, and I could post it. You can just watch it at home. Yeah, that's fine. So what I'm going to do instead now is you guys can take out your Chromebooks, or you both have them out. I'm going to actually post some typers. You guys remember the typers? We haven't done that many of them, but probably remember them. I'm going to post some typers for you to work on now in some groups, because usually physics teachers use those as conceptual questions, but usually they would put people in groups because it generally generates some good discussion, because you get students disagreeing about certain things. So we're going to do that. I'll spend the remainder of class, but you spend the remainder of class working on a class time assignment that I will post in just one moment. And then, like I said, the elevator problem is the next special problem. I'll record that during my break today, and then I'll post it for you to watch. Should be about 20 to maybe 25 minutes. There's not that many left. I'm eventually, pretty soon, going to go down my list in my head and just think, did this, did this, did this, did this. We're getting pretty close to covering most of these types of problems you need to know. And then, oh yeah, and then there's the other comment. There's going to be a quiz. So I am going to give you guys a quiz on Thursday in class. So it's going to be just 10 problems from AP Classroom. So you're going to have to make sure you have your Chromebooks, available, and you can use those. Because again, some people at home might be using other devices, but you don't have the lockdown browser figured out on that device. So just make sure whatever you've been doing for, and I think there are a couple of you that managed to get it to work somehow on your own personal device, but I don't think 90% of you, I think, are using your Chromebooks for that. Just know that that's what I'm doing with you on Thursday. It's only going to be 30 minutes. I'm going to give you 30 minutes to do 10 problems. That's generous because by the end of the year, AP exam, you have to be able to do each problem in an average of 1 minute and 50 seconds on average. Of course, some slightly longer, some slightly less. If I'm giving you 10 problems and giving you 30 minutes, then the average is 3 minutes, right? Which is generous. But it's still relatively early in the year. Not early, but it's not the end of the year. So I'm going to give you a little extra time, but just know that it is going to be timed. You get 10 questions. They're going to be on AP Classroom. I have not even picked them out yet. I'm reminding myself now that I have to do that. And that will be given in the beginning of class where you'll log in for those 2 of you that are here, and then the rest are at home. And you'll have 30 minutes, and then it will lock and close after that 30 minutes. And that will be specifically on forces and Newton's laws of motions. You'll very likely see a lot of the problems that we've covered. Because when I go through their library, I see all those problems. I see the elevator problem. I see the box against the wall. I see the inclined plane. I see all the things that I'm showing you. You're more than likely going to recognize all of them, more than likely. So in an attempt to review for that, I'd recommend going over those problems that I've been going over with you. All right. Bounce over here now. All right. Let's see. Period 6, classwork. We create Piper's dynamics. Let me see if I can find it. I believe I posted on my, oh yeah, it's in my Typer folder. Yep, right there. Okay, so I'm gonna go back. Add. File. Browse. Desktop. Typer. All right. Due date. Let's make it the next class. No, make it next week, or I don't know, make it Sunday. It's Sunday. No, make it Monday. I'll make it Monday. Shouldn't be up till midnight, but that's what it's going to be. So the due date for this will be Sunday at midnight. There's like 5, I think, in there. I'm not sure, 100%. We'll see in a minute. 5 or 6. And I thought I just added it, but it's not there. Try again. Papers. Not showing. All right, let me assign it and see what happens. Let me do this for both you and period 8. See, oh yeah, it's there. It's 2 of them. So you can go ahead and open those, and maybe I'm gonna pop you guys into some groups. You have about 20 minutes left. You can work on some of them together, or on your own, or whatever you choose. But generally, the idea again is that you work with each other, talk at least about some of them. There's 1, 2. Well, when I said 5, I was thinking 5 pages. Looks like there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there was actually 6 pages, not 5 pages, and there's 2 on each. They're all ranking tasks. They're all rank such and such in order from greatest to least. So I'm pretty sure all of them are that way. That's good. Some of them are actually, really make you think, though. You had a question, Miles? It's what? Yeah, I do. I want you guys both to join the meet. All right, I'm going to throw you into your groups now. I don't have to be presenting anymore. Here, breakout rooms. All right, set up breakout rooms. 1, 2, 3. That works. All right. So that's what you guys are working on. Any questions? Last 20 minutes, work on some typers. All right, I'm going to pop you into your rooms.